Okay, so today we are going to talk about the work done by a constant force and a variable force. Okay, so let's suppose we have some constant force which displaces an object. Okay, so from some initial position, let's call it A, to some final position. So if I want to draw a constant force versus the displacement graph, how will it look like? So on y-axis or the vertical axis, I have constant force, and on x-axis or the horizontal axis, I have suppose the position. Okay, so the graph of constant force versus the position will look like this, right? It will look like this. And suppose this force acts on the body till some position, so from some position A to some position B. Okay, so this force acts on the body from some position A to some position B. So this is my A, x equals to A. This is my x equals to B. Okay, so what will be work done by this force? We are considering one dimensional force only. What will be work done by this force? It is just force multiplied by displacement, right? So if the force and displacement, they are in same direction, what will be the work done? Force into displacement, right? Yes, no? So work here, when the object is displaced from A to B, W is equal to what? F multiplied by position at point B minus position at point A. That's the displacement. Okay, so it is x at B minus x at A, or you can say B minus A. And what will be that? So if you consider this rectangle, let's call it ABCD, on this force versus displacement, force versus position curve. Okay, it will be area under this curve, right? It will be area under this force versus displacement curve. So this is clear. Okay, this is very simple, right? So instead of a constant force, now suppose we have a variable force. Okay, we have a variable force. So now force is not constant. So we are considering one dimensional force only, but it is variable. So this force will be some function of position. Okay, force will be function of time, and it will be function of position also. So I'm plotting graph of this force versus the position, and now I want to find out the work done from this position to this position. So what will be that? This is x equals to A, this is x equals to B. What will be that work? Yes, it will be again area under this curve, right? It will be this much area. Okay, it will be this much area, right? So what can I say? The area under force versus position curve, the area under force versus position curve gives the work done, right? Yes, no? Okay, and how will we find out this area? So this is simple, integration, right? Yes, Tamil Selvi, how will we find out this area? We'll integrate. Okay, so I will just explain it in very short. So let's suppose the force at this position, x equal to A. It is suppose force at this position it's suppose f of x, right? Force at this position is f of x. And now let's suppose this object is displaced by very small displacement. So for very small displacement, you can consider that this force will remain constant. Okay, so for a small work, from, you can say, x equals to a to x equals to a plus dx, displacement is how much? It is dx. We can say that force remains constant, force is fairly constant. Okay, if displacement is very small, and therefore we can say the work is equal to, dw is the work, it is equal to f dot dx, right? So if you take very small displacement, so you can say force doesn't change much. Okay, force doesn't change much, right? So then you take this point, and actually here it's changing. Okay, but we are considering very small displacement that I cannot show on this graph. Okay, so force, you can say it will change, but the change will be very little. Okay, infinitesimally small, right? So this is f of x, this is f of x plus dx. Okay, so how much will be work done from here to here? Work done will be area under this small rectangle. Okay, it will be area under this small rectangle. So this much area, we can say, this much will be the work done. So if we break down the total area into n number of small pieces and add the areas of all the rectangles, okay, which make the total area, then we'll get what? The total area under the curve. Okay, but there will be some error. And how can we reduce the error? So when we break the total area into many small pieces, okay, if number of pieces is made very large, then this displacement will be very short. All right, so when the total area is divided into more number of pieces, what will happen? The error will get reduced. Okay, so if n tends to infinity, okay, that means number of pieces becomes very large, then this error will become what? It will become almost zero. And that procedure of taking n equals to infinity and adding all the areas, okay, all these small pieces, areas of all these small pieces, it is known as what? It is known as the integral. Okay, so we have seen this several times now. So the total work done when the object is displaced from a to b, when object is displaced from a to b, will be what? It is integral, let's say it is w, so it is integral of dw from a to b. Okay, so it is equal to what? Integral from a to b of f dot dx, right? And graphically it is shown like this. It is area under force versus position graph, and mathematically it is what? The integral of f dot dx from a to b. That's the work done for a variable force. Okay, so this is in one dimension. We can generalize it for 2 dimensions, 3 dimensions, right? If I want to generalize this, then force can be function of, okay, force can be function of xyz, not just not just x or y or z. It can be a function of xyz, right? Okay, and it's a vector quantity. Force is a vector quantity. So f bar is suppose function of xyz. Then how much would be work done to displace the object from some position to some other position? Okay, if we take small displacement, so for small displacement, dr bar how much would be the work done? Work done dW is equal to what? It is dot product. We have studied about it. Work done is dot product of force and displacement for the constant force. Okay, but this force is position dependent. So for small displacement, very small displacement, we can say that force remains almost constant. So for very small displacement, I can take dot product of force and displacement. Okay, but this is equal to what? There are three components. Sorry, there are three components to force as well as the displacement. So the force can be written as Fx, the x component, multiplied by I cap, plus Fy, the y component, multiplied by j cap, plus Fz times k cap. And similarly, the displacement will also have three components. So it is dx times I cap, plus dy times j cap, plus dz times k cap, right? So now you multiply this. So what will you get? You will get Fx dx I cap dot I cap is equal to 1 plus Fy dy plus Fz dz, right? Yes, no? Okay. And your total work done from some initial position to final position. So the total work done from some initial position to final position, W is equal to integral of dW, we know. So from R initial, you can say R initial, okay, or let's call it R1 only, to R2 bar, okay, and that is equal to, now dW has these three terms, fx dx, fy dy, fz dz. So you want to take its integral from R1 bar to R2 bar. So this integral will also have three terms now. There will be three. So we can break down this integral into three pieces. Okay. So what will be those three pieces? So it is fx dx, the integral of the integral of fx dx from x1 to x2. Okay, from initial x coordinate to final x coordinate, plus integral of fy dy from y1 to y2, plus the integral of fz dz from z1 to z2, right? It will have these three integrals. Okay, one for x direction, one for y direction, one for displacement in z direction. No, this is just generalization. Okay, so there haven't been questions based upon this in the NEET exam, but that doesn't mean it might not come. Okay, it will not come. It might be there. Okay, because this is not a complicated topic, right? And in JEE there have been lots of questions. Okay, all right. So let us see some questions. So this question: force F on a particle moving in a straight line varies with distance d as shown in the figure. The work done on the particle during its displacement of 12 meters is. So this is from NEET 2011. Very simple question. Tell me the answer. So we know work done is equal to what? Area under force versus position curve, or force versus, yes, 13 joules. Right. It is area of this rectangle and area of this triangle. So area of this rectangle, okay, it is half of base multiplied, sorry, area of the triangle is half of base multiplied by height. Area of the rectangle is base multiplied by height. Okay, so 7 minus 3, 4, 4 times 2. So this is 8, and this is how much? 12 minus 7 is 5. 5 multiplied by 2 divided by 2. Yeah, so it is 5. So 8 plus 5, 13 joules. Okay, this was very simple. This is simple. right? So this question is a force acting on an object varies with distance x as shown. The force in Newton and x is in meter. Was it given in last question? Yes. So units were given along x and y axis. The work done by the force in moving the object from x equal to 0 to x equal to 6 meters is x equal to 0 to x equal to 6. So this is similar question, right? So 3 times 3, 9 plus how much? 3 times 3, half of that, 4.5. So 9 plus 4.5, 13.5. Okay, so option B is the answer. All right. Then next question. This is from NEET 2019. A force 20 plus 10y acts on a particle in y direction where F is in Newton and y in meter. The work done by this force to move the particle from y equals to 0 to y equals to 1 meter is. Okay, so now what do we have to do? This is one-dimensional problem. So F is function of y only and displacement is also in y direction. Okay, so the work done is equal to integral of F dot dy, right? From y equals to 0 to y equals to 1. So from 0 to 1. And it is equal to integral of 20 plus 10y dy from 0 to 1. Okay, so that's value of force only, 20 plus 10y. And you can separate this into two integrals. So it is 20 dy, integral of this from 0 to 1, plus integral of 10y dy from 0 to 1. Okay, and that is equal to integral of 20 dy. So 20 you can take out, integral of dy is y. Okay, so 20 times y from 0 to 1 plus 10 you can take out from the second integral, and integral of y dy is y square upon 2. So y square divided by 2, y square upon 2 from 0 to 1. So how much is this? Substitute the upper and lower limits. So 20 times y, okay, y only. So when y is equal to 1 minus y equals to 0, plus you can divide by this 2, so it is 10 by 2, 5. So 5 multiplied by y square is 1 minus what? 0. 1 square minus 0 square. Okay, or 1 minus 0 again. So how much is the answer? 20 plus 5. 25 joules is the answer. So repeated in 1992, 1994. Okay, same question with same values. A position dependent force. You solved it so fast. Oh, very good. So a position dependent force F equals to this thing acts on a body of mass 2 kg and displaces from 0 x equal to 0 to 5 newtons. The work done in joule is. Okay, so let me solve. It is integral of f dot dx from 0 to 5. Okay, so it is, how much is f? F is 7 minus 2x plus 3x square. Okay, from 0 to 5 dx, and it's equal to 7 you can take out, integral of dx from 0 to 5 minus 2 you can take out x dx from 0 to 5 plus 3 you can take out, it is x square dx from 0 to 5. All right, so it is equal to, work done is equal to integral of dx is x, 5 minus 0. So 7 multiplied by 5 minus 0 minus 2 multiplied by, it is x square upon 2. Okay, from 0 to 5, and plus it is 3 times x cube divided by 3. Okay, integral of x square dx is x cube upon 3 from 0 to 5. All right, so this is equal to W is equal to 35 minus this 2 and 2 gets cancelled. So 5 square is 25 minus 25 and plus 3 gets cancelled. 5 cube is 125. 135, right? Okay, very good. Anyways, so let's talk about the kinetic energy. So we have been talking about the kinetic energy since, I guess, since sixth standard or something, right? So in seventh standard book also there are formulae. Kinetic energy is half of mv square. Okay, if not sixth, seventh at least. Yes, no? And in nine there is a chapter on this. All right. Okay, so let's talk about kinetic energy once again. So what is kinetic energy? It is energy possessed by a body due to its motion. Okay, energy possessed by a body due to its motion, and we know the formula for kinetic energy is half of m times v square. Okay, and I'm sorry. So, and you can express this formula in another form if you take into consideration momentum of a body. P is equal to mv. Okay, so what will I do? I will just multiply and divide by m here. So it is half of m, sorry, yeah, I will just multiply and divide by m. So it is half of m times m into v square divided by m. Okay, I have just multiplied and divided by m. So this will be m square v square. Okay, so this is m square v square. That means it is square of mv square. Okay, divided by m. Or what is mv? It is momentum. So you can write kinetic energy equals to what? P square divided by 2m. So this is another formula for kinetic energy, right? Sorry. Okay, so we have this formula for kinetic energy. Kinetic energy equals to half of mv square, and kinetic energy equals to p square divided by 2m. This is another formula. Okay, so there have been questions surprisingly based upon this formula and this formula also, so which are very simple. Okay, so let's solve some questions based upon kinetic energy. So a particle of mass m1 is moving with velocity v1. Okay, it's moving with velocity v1, and another particle of mass m2 is moving with velocity v2. Both of them have same momentum, but their different kinetic energies are E1 and E2 respectively. If m1 is greater than m2, then E1 is less than E2, or E2 by E1 upon E2 is m1 upon m2. E1 is greater than E2, or E1 equals to E2. This is from 2004. So which is the answer? This is very straightforward. Okay, see, the bodies have same momentum. That means we have to consider which formula for kinetic energy? The formula in terms of momentum, right? So kinetic energy, let's denote it by E. It is p square upon 2m. Okay, momentum is same, so energy is inversely proportional to mass, right? Energy is inversely proportional to mass. Kinetic energy is inversely proportional to mass. So if mass is more, energy will be less. If mass is less, energy will be more. So what's the answer? M1 is greater than M2. So E1 would be less than E2. Right? This is the answer. Okay. So this is actually what can we say? So this thing should come into the mind very instantaneously. Okay, E equals to p square upon 2m. Just like when we say kinetic energy, two formulas should come to our mind now. Okay, one is half of mv square, second is p square upon 2m. Okay, so whether the velocity is given or the momentum is given, depending upon that. So momentum is given, momentum is same. Kinetic energy is inversely proportional to mass now because momentum is equal. Okay, so we have to use this formula. So if mass is more, energy will be less. If mass is less, energy will be more. So since m1 is greater than m2, e1 will be less than e2. Next question. These are all NEET questions. Okay, very simple. Okay, so if kinetic energy of a body is increased by 300%, then the percentage change in momentum will be. So again, this is simple, right? Kinetic energy is increased by 300%. Okay, so we can say K2 upon K1 equals to how much? What will be the ratio? If it increases by 300%, that means K2 is 400%. Okay, so K2 will be 400% of K1. Okay, increment is 300%. Okay, so K2 equals to K1 plus how much? 300% of K1. Okay, I'm sorry. So K2 equals to what? K1 plus 300% of K1. So 300% means what? 3 times K1. If K1 is 100%, 300% is 3 times K1. So K2 is equal to what? How much? It is 4 times K1. Okay. And you know that it is equal to what? P2 square upon 2 times M upon P1 square upon 2 times M. Right? Yes, no? Okay. So mass and mass will get cancelled and you have, or you can directly say it is directly proportional to momentum square. Okay, because mass will not change. So P2 upon P1 square is equal to 4 upon 1. And therefore, how much will be P2 upon P1? Take square root. It is 2 upon 1. So if P1 is 100%, how much would be P2? So P2 is 200% of P1. I'm sorry. So P2 is 200% of P1, or P2 equals to 2 times P1. So how much is the increment? Increment is 100%. Right? Okay, good. So it's again extremely simple problem. Okay, and you don't have to do all this, right? You can do it in your mind. Kinetic energy increases by 300%. Okay, that means final kinetic energy is 400% of initial kinetic energy, or you can say it is 4 times initial kinetic energy. Okay, and directly you can say that kinetic energy is directly proportional to momentum square. So you can directly write down, okay, K2 by K1 is equal to what? P2 by P1 square. Okay, and then you can put K2 upon K1 equals to 4 is to 1. So P2 by P1 is equal to what? 2 is to 1. The problem solved. Let's move on to the next problem. So two bodies with kinetic energies in the ratio 4 is to 1 are moving with equal linear momentum. The ratio of their masses is, see how many questions have been asked based upon this. Okay, so two bodies with kinetic energies in ratio 4 is to 1 are moving with equal linear momentum, right? The ratio of their masses is 1 is to 4. Very good, Sanjay. Okay, so momentum is given. That means you will use which formula? You will use P square upon 2m. So this is kinetic energy, or I can write K. Generally I use K only. So K1 equals to P square upon 2m1, K2 equals to P square upon 2m2. Okay, K2 equals to P square upon 2m2, right? So momentum is given to be equal. So that means you can directly use this relation. The kinetic energy is inversely proportional to mass. Okay, so K1 upon K2 equals to m2 upon m1, because they are inversely proportional. Okay, and you are given K1 by K2, which is 4 is to 1. So m2 upon m1 will be 4 is to 1. So m1 upon m2 or m1 is to m2 will be what? 1 is to 4. Okay, very simple. Option D. Right? All right. Let's see next question. Oh, can you see this? Okay. So 1989, 1997, 1998. They repeated it 3 times. And okay. So two bodies of masses. Okay. So did you have this perception that questions are not repeated in the NEET exam? Yes, no? Okay. So questions are repeated. We are seeing that questions are repeated lot of times. Okay. So questions will be either same. Okay. They are not most of the times not repeated word to word. So what is done? They will change the values. Okay. Either they will change the value or they will tweak it a little bit. Right. All right, so this is very simple question. Two bodies of masses m1 and 4m, m and 4m are moving with equal kinetic energies. The ratio of their linear momenta is. So again, we'll use kinetic energy K1 is to K2 equals to what? P1 square upon 2m1, and we'll use this a lot, that dividing by something is equal to what? Multiplying by its reciprocal. So 2 times m2 upon P2 square. Okay, so this will simplify the process. Okay, so this is very simple. K1 upon K2, the two bodies are moving with equal kinetic energy. So this is one. That means you are given what? With masses. M1 is to M2 is how much? 1 is to 4. Okay, so you have P1 square upon P2 square, or P1 by P2 square. So M2 is 4 times M1. 4m divided by m. So m and m get cancelled. You can take that 4 on the other side. It goes into the denominator. So P1 by P2 square is 1 by 4. So what's the ratio of P1 is to P2? 1 by 2. So let's see this next question. This is repeated 1997, 2001. A particle is projected making an angle 45 degrees with the horizontal having kinetic energy K. The kinetic energy at the highest point will be. Tell me. We have solved these kind of questions. Okay, similar questions in projectile motion. It will be k by 2. Or did you forget? So it is projected making an angle 45 degrees. Okay, making an angle 45 degrees with the horizontal. So how much would be its x component and y component of velocity? U cos theta, u sin theta, right? So for 45 degrees, cos theta and sin theta is equal, right? It is 1 upon root 2, 1 upon root 2. Okay, so this will be u sin theta, that is u upon root 2, because sine of 45 is 1 upon root 2, and this will be u cos theta, which is 1 upon root 2. So x component of velocity is u upon root 2, y component of velocity is also u upon root 2. Okay, and what happens at the topmost position? The body will have only x component of velocity, right? So kinetic energy here will be equal to half of m into ux square only. So let's call it k at h, and this is original k. Okay, so it is half of m into ux square, and how much is ux? U upon root 2 square, so that is u square upon 2, or you can say it is equal to what? Take that 2 out, so it will be 2 times half of mu square. Okay, so it is 2 times, or not 2 times, half times half of mu square. Okay, so that is half of initial kinetic energy, right? So let's see this next question. A ball of mass 2 kg and another of mass 4 kg are dropped together from a 60 feet tall building. Okay, so they are dropped together from a 60 feet tall building. After a fall of 30 feet, each towards earth, their respective kinetic energies will be in the ratio of. Tell me. This is simple, right? See, there are two masses. They are dropped from some height, same height. Okay. So, does their acceleration depend on their masses? No, right? It doesn't depend on mass. Okay, both of them will fall with same acceleration, which is acceleration due to gravity. Okay, so therefore, so now after a fall of 30 feet each towards earth, so they are falling to 30 feet each towards earth, their velocities will be equal. Yes, no? And if velocities are equal, then kinetic energy, so it depends on mass only now. Okay, I mean the relative kinetic energy depends on the mass only. So their masses are 2 kg and 4 kg. So after a fall of 30 feet each, okay, their velocities will be equal. Velocities at this point will be equal because both of them will fall with same acceleration, which is acceleration due to gravity. So since velocities are equal, kinetic energies are in the ratio of what? Ratio of masses only. So mass is 2 kg and 4 kg. So kinetic energies K1 is to K2 is equal to M1 is to M2 only. Okay, so that is 1 is to 2. This is the answer. Yes, no?